Hey, I want to ask this question. Raise your hand if you've heard of Qualcomm. That's pretty good. So you either done your homework or our name is out there. So Qualcomm's been around for 40 years. I've been there for 37 years. I joined when it was a baby company. When I was here at Purdue, I did my master's degree. I taught, I think, something that many of you may hit last year, which was the circuits lab next year. And then I went up, after 1 quarter of that, taught the communications lab for basically about 1.5 years. So I'm going to talk a little bit about Qualcomm. Okay, I'm going to go to the first slide. I guess I need to push this button. Actually, I'm going to do that. That's easier. I'm going to take us way back to 1963. Okay, an important picture. This was the world's first sequential decoder, built at MIT Lincoln Laboratory, and I'm going to talk a little bit about that. Now, to give you perspective, that's 5 racks. That is not, it's smaller than a pinhead on our chip today. We don't build those, we build a Viterbi decoder. It's more like the other end of the pin on our chip today. Okay, I wanted to point this out because of really one important thing, and the person in the middle you should know of. A guy named Claude Shannon. Anybody hear of him? Okay, his master's thesis was critically important in this area. He showed that Boolean algebra was what you could design logic with. It's fundamental pinnings of mathematics in terms of logic design. He's even more better known for my area, which is the mathematical theory of communication, which showed what is the fundamental capacity of a communications channel. Okay, it's the bandwidth times the log of 1 plus the signal-to-noise ratio. Very fundamental thing. He was also one of the key pioneers of cryptography. And he was one of the creators of the Dartmouth Conference on AI. How many have heard of that? Very first real discussion where the term AI came from in 1958. The guy on the right, okay, is a guy named Jack Wozencraft, famous guy. He wrote the book with one of the founders of Qualcomm, which was used for communications teaching for many years. This type of machine was succeeded by the other founder of Qualcomm, Andrew Viterbi, who came up with an optimal decoder for this type of error-correcting codes. That's our history. Our history was communications, but there's an important part of chips. In 1989, we demonstrated what was the beginning of modern cellular communications by basically, without getting into the details of that, how do we work? For this, we won the IEEE Milestone Award for that. But this became the basic standard for cellular in much of the United States, okay, and around the world, and then became the basis for what we call 3G cellular in terms of technology and such on. This has, by the way, been my area of primary work in the company. But we would have not been successful if we had not had the intermix between communication guys like me and chip guys. At that time, we were a small company. This little smallest chip there, by basically 1991, replaced those 5 racks. Okay, we were able to be successful because we brought modern communications technology and also knew how to put it into silicon, fusing the two together. And we continue to do this today through everything. By the way, that's 1.2 micron technology. Where are we now? 3? What? Going down to 2 and all that. What?
Nanometer?
Yeah, nanometer. Yeah, not micron. That's going the wrong way. Sorry, we think we're all in nanometers today. So I just wanted to point that out, plus some other chips. So let me just talk about Qualcomm. So what we're really known for, as I mentioned, was creating the Gs of cellular telephone. We not only brought this basic design of the first standard, but really fusing semiconductor technology with communications technology in an advanced way, okay? Plus also turned the industry around to think about how do you use very sophisticated techniques in designing communication systems? And we have been at the forefront of cell phones, Wi-Fi, Bluetooth technology, and we're going to talk about some of the latest things here in a minute. Since then, I'm working on 6G. Probably not even heard of it, but you've heard of 5G, you've heard of 4G LTE, etc. So, let me just show you at a very high level. Joe's going to get into how you actually design these things, okay, in a little bit. What was fundamentally on it? So we build, and we're probably the company that's probably building the most sophisticated system on a chip today. So we have a bunch of CPUs. I'll show you a little bit more there later. GPUs, neural processors, a lot of memory. Then we have image signal processors. This is what your cell phone, this is what, when you take a photo with your camera, or you try to take a video, that's what does the basic processing. Okay, we have modems. Okay, that's the communications part. Actually, there's also display processors. There's all sorts of other things on there in addition to that. But that's sort of at a high level. Now we talk about this. Here's our latest chip, and I'm only going to have time for this one thing. Look at the CPUs that we have on that today. Our first phones had ADC 186. Really pretty darn slow. The growth of processing on a cell phone, a lot by what we put on it, has almost been exponential since the early 1990s. There. I'm not going to say too much, but this is all sort of the key things of what's going on a modern cell phone chip in terms of some of the stuff. Data, you can run it up to 12.5 gigabits if you can get if you can get the great coverage from the cell site. Lots of processing and all of that. Hey, whoops, went the wrong way. Now, I've been talking about cell phones. I can do that same discussion. That's the mobile space. We're now into PCs, okay? So if you hear of a Snapdragon PC, that's our stuff, okay? Moving basically a ARM processor, not an Intel x86, into a PC. Okay, spatial computing, goggles, okay? Think Oculus and all the other guys out there. Qualcomm chips, okay? AI wearables, your watches, many of your earbuds, etc. Automobile. We started off with communications to a car, then realized that, oops, those display units and all are basically run by, are very, very similar to what's in a cell phone. They need cameras, they need displays. Now there's a whole line of chips and actually running automated driving for a lot of cars. Okay, edge networking. You have a PC, an access point in your house, maybe Qualcomm chips involved. And certainly the ones probably around here, I have to look at who made them, may have Qualcomm chips inside. IoT, big. AI, big. And I'm going to leave it at that. Joe. Ooh, he needs to get mic'd up.
All right, now it's my turn. So thanks, Ed. Yeah, Qualcomm is a hardware company, and so now I'm going to kind of dive into a little bit about how we design these chips to go into the various marketplaces. Before that, just an introduction of myself. I'm graduated from Purdue about 25 or so years ago. I went through freshman engineering. I wanted to be either aeronautical, chemical, or computer engineering. I liked programming, went into computer engineering, got an internship with Intel while I was a Purdue student, and that got me on the chip design track, and I found it just fascinating ever since. And so it's a little bit on my background, but just want to talk about kind of the design process at Qualcomm. You know, one of the main things that enables us to deliver these products into so many markets is our vast portfolio of technology and what we call IP. IP is intellectual property, but In the hardware world, we use that term for the actual components like CPUs and GPUs and NPUs that go into an SoC, into the chip itself, to provide that capability and that functionality. Qualcomm has a vast portfolio for connectivity, for sensing, for compute. Within Qualcomm, there's dedicated research and development teams in all of these areas so that we can build this critical IP and build the best-in-class SoCs, chips in the marketplace. So I wanted to talk a little bit about kind of the components of edge compute and edge AI. AI, of course, is the hot topic these days, and Qualcomm strongly believes in the fact that AI is going to be on the edge, in our hands, on the mobile devices, in our laptops. It's really going to move in that direction, away from the cloud, away from the big data centers of AI. And in chip architecture, there's kind of three major components today that are critical for delivering this AI capability. The CPU, of course, is a critical piece, and Ed touched on the multiple cores, the multiple processors that we embed in our designs. CPU is a pretty fundamental thing to build the framework and drive the content of these AI models. But there's two other major compute elements that are also very critical. I'm sure most of you have heard of GPUs and their role in AI. They're very much like CPUs because they are programmable. You can write code that runs on a GPU. You can write shaders. You can write compute shaders. The main benefit GPUs provide is they execute multiple things in parallel at the same time. And that type of operation is really good for neural networks, which are kind of the fundamental mechanics of an AI model. And so that's why GPUs have been very relevant in the deployment of AI, is because they have that kind of parallel processing mechanism. The third type of processor that Qualcomm has as IP and integrates into their chips is an NPU. And an NPU is a very specialized function processor that has a lot of these math units that are necessary for neural networks. So it's really built specifically for neural networks and AI. So it's very efficient, very fast, low latency, and that is really the best place to run an AI model once it's trained. But all three of these are really critical in delivering that capability to you on the phone. And Qualcomm has really the best in class for all of these components, and we have really extensive design and research teams to continually to push the edge and the boundary of the capabilities of these processors, of these IP blocks. But in the end, we're a silicon chip provider, so we sell a chip to our customers. And what that chip is for us is an SoC. It's a system on a chip. And a system on a chip is really an integration of all of these key IPs and technologies into a single device that then works together as a single system. And that one chip provides all of these capabilities. If you looked at the early cell phones, it was multiple chips to provide these various functions, and it was tied together on a board. Qualcomm is one of the best innovators to do that integration of pulling these capabilities and these technologies together into a single chip, and it's called an SoC. And so we do our IP development. We design CPUs and GPUs. But then we also have SoC design teams that focus on the integration, pulling those pieces together to build the whole system. And that in itself is very complicated to understand the capabilities and requirements of these building blocks, to make them work and talk together, to fit the power and area requirements that are necessary for that particular chip that's being built. And so this is also a key sort of design and development element within Qualcomm. Just a kind of high level about chip design, IP design. There's kind of this triangle on the side. There's kind of two things. There's features, which is what is the chip capable of doing, right? Like, does it have the display? Does it have the processing power? Does it run these models? Does it what does it do? That's kind of the features that a chip provides. But in a mobile platform and many of the platforms that we deal with today, many silicon devices we deal with today, it needs to be low power. It needs to meet certain criteria. And the triangle is a key kind of design criteria that we focus on in the industry. It's power, perf, and area. We need to balance we need the highest performance, we need the lowest power, and we need to fit into the given area of silicon to implement our features. Traditional design is figure out the features, build the design, get it to work, and then go figure out how to dial the knobs to get into the right kind of PPA, the right power, perf, and area. But really, to get the most efficiency, you need to think about that up front. You make the power, perf, and area part of the product definition. And so at the beginning, as you define the features, you define what your performance criteria is, what your power limits are, what your area allocation is, and you design according to that requirement. And so this is a very important part of the Qualcomm design process of really any SoC and modern design processes is really focusing those areas as just as critical as the features themselves. So kind of I'll dive a little bit into design itself, kind of what are the activities, what are the roles that are involved in chip design. And it kind of fits in the middle of, we've got definition, and this comes from the product teams that look at the market to understand what does this chip need to do, what is its capabilities, what are customers asking for in terms of a product. And so that definition comes from a lot of sources. And so that process kind of feeds into how we design and what needs to be designed. But then once you get into the design process itself, that arrow that goes into design, you can say that's the spec. That's the specification of what the design is supposed to do. Within design, there's a lot of roles to go from that spec to an actual silicon implementation. And so there's the architecture step, which takes that spec and figures out how do we kind of build the data paths and the control logic and the sub pieces to actually implement those features. We have microarchitecture that then figures out those minute details of how to use logic to implement those components and those data paths. And then you design it, and that's a whole role in itself in that you use RTL, a design language, to specify the definition of your logic that will turn into the hardware design itself. And it's not only specifying it in that language, but you have to synthesize it into logic gates. You have to take it through timing and power and area analysis. So you have to then figure out how you're taking your block diagram and turning it into actual silicon design. Then within, even before you create that silicon, create that chip, you have to test it. Because if you don't test it and you find a bug, it's many months later and many more millions of dollars to get another chip taped out and fabricated. And so in this design phase, you spend a lot of time testing. And we have a lot of different platforms, and I'll get into it in a bit. that becomes a major component of the design process is testing and verifying, making sure that what you've designed and implemented is going to do what it's supposed to do. It meets the spec requirement, it works functionally, it is bug-free. We do a lot more testing in hardware design than software developers do, because software, if it's wrong, you can send a patch out, and that's pretty fluid and pretty quick. If you do it wrong in hardware, that's a respin, and respins are expensive. Refabricating a new chip design is, like I said, many millions of dollars and many more months in your timeline. So verification is a big component. Then we have physical design, and physical design is really kind of taking that language description of the design and taking it through the process to sort of a final database, a final definition of how the transistors are defined on a silicon wafer. And that database, getting from the logical representation to that database, there's a lot of work there. There's a lot of thermal, mechanical, elemental checks to make sure that what your tooling has done to get you to that silicon implementation is correct and will work once you get that silicon. And then we send it to manufacturers. So there's fabs, TSMC, Samsung, Intel. They fab chips. They're the ones that actually manufacture. There's a lot of downstream companies that do the packaging, doing the silicon testing. We work with them as partners, and we deliver the design to them, and they go manufacture and create that chip for us, and then we get the chip back, and we sell the chip, so the packaged chip. So that is kind of the downstream part of the chip making process after the design phase. I'll kind of go into a little bit more detail. I know there's a lot of words. I'll try to just kind of explain, but kind of talking more about the different phases I touched on before in terms of the design activities and sort of what's involved in that activity, but also what are the skill sets needed in those activities, and kind of also what are the tools used for that role. So, in the architecture and modeling role, that's kind of the first one. They're the ones that take the spec, figure out how to make it into a logical implementation that can be built in silicon. They use a lot of high-level languages. They use C and C++, and other languages to model the design. So they're creating an implementation that can be tested and analyzed to determine, is this the right way to do it, before we go and start making it into a silicon design. And so there's a lot of programming and analysis tools and plotting and extraction to make sure this is the right thing that we're doing. Sort of the main skills here, like coding skills, but also kind of understanding standards and specs. Most of the time, architects have been in the industry for quite a few years and have gone through multiple product cycles and know kind of the lay of the land and what's kind of needed. And so this role is comes from experience as well. The next role is kind of microarchitecture and design. This is the step where we take sort of the block diagram of how the chip works and how it's connected and the functions in each block, and then they go and actually figure out how to implement that in the language that specifies the hardware, and that's called RTL, Registered Transfer Language. And so, that takes some, coding skills, but kind of a specific type of coding skills. They use a lot of analysis tools and tools that generate take their code and generate it into, the low-level construct that's going to turn into the silicon chip. So, verification, like I said, is a very key component of the process, and verification builds test benches and test structures to verify the design. So they, spend a lot more time coding actually in software languages. So there's a lot of software skills necessary for verification. And they build test cases to exercise the design, run it through sort of different scenarios and make sure it works correctly. And this is a role that kind of spans sort of a hardware and software skill set, because you need software skills to build the tests, but you need to understand the underlying hardware and understand the right ways to kind of break the design and find bugs. And there's a lot of interesting techniques and technologies used, including simulation, emulation, formal methods in that verification role. Physical design, that takes sort of the logical representation and they take it through a number of different tools to get to that final database that can go to the fab and turn into a silicon chip. There's a lot of things around, timing, meeting the timing so it runs at the target frequency, area, power, those PPA things that I talked about. Physical design is very focused on getting kind of the best result out of a very complicated tool chain to get that final database that becomes a chip. And then I put in here also, there's a lot of software, firmware, compiler work that goes into a design team as well. Because hardware doesn't just work in a vacuum. You need software running in a processor or something to light up that hardware and to make it work. And so we have a lot of teams that are software developers by background, but have learned hardware and understand how to interact with hardware and build the right low-level software to light up hardware and make it work. It's a unique skill set. It's software background, but it's very hardware-centric. And so, but this is also a very critical role and skill set because, like I said, without software, your hardware doesn't work. So these are kind of the key sort of development areas in chip design process. Kind of final point, kind of focused on verification, but also, the importance of making sure the chip works before it goes and becomes, actual silicon. The need to make sure that it works, that it is bug-free, runs at the performance that we expect it to. There's a lot of effort and work, and there's a lot of neat kind of platforms that are used for this. So, we have RTL simulation, which is a software simulation of the design that can kind of run through scenarios and tells you if it works or not. There's a lot of performance and benchmark analysis, so we run benchmarks and other test suites against the design to make sure it works properly. Formal verification is a mathematical expansion of the design to see if there is a bug that exists in the design. Hardware emulation, we use hardware to verify hardware. So hardware emulation, there are these big machines that have arrays of processors and custom components that model the hardware. So we can take our design before it's silicon, we load it into this emulator. We can run it at maybe 1/10 of the speed, but you get to boot in OS, you get to do a lot of stuff on the hardware before you go tape it out in this emulation environment. Similar to that is FPGA prototyping. FPGAs are programmable arrays, and you can fit the design into an FPGA, then you can use that as well as a pre-silicon verification vehicle. But then once you get the silicon, once it's available, after fabrication, there's still a lot of testing and validation that needs to occur. And so we get it in the lab, we run tests, we run through a lot of different things, not only for functionality to make sure the features work properly, but performance characterization, timing characterization, a lot of things to deal with the electrical characteristics of the design are measured in this environment. So that is kind of a high-level overview of various aspects of the hardware design process, and that's all that I've got. Unless Ed has any more.
Thank you, Ed and Joe. Do you have any question right now before I? Okay, so we actually have some questions that student pre-submitted, and I found it interesting, especially like we received a lot of or we heard a lot about like the news nowadays. So the question is, how does Qualcomm's reliance on chip foundries dictate its reliance on international policy and trade restrictions as we see in today's global markets?
Ed?
I have a mic.
Can you use that one? Yeah.
Does this get both online and in here? This is online?
Yeah, it's for.
Okay, that's online. So let me try to speak up. If the camera can't hear me, shout. Wow, you asked one of the most complicated questions out there. I think it's pretty well known that the fabs that are capable of doing, I will call it the most advanced nodes, are basically TSMC in Taiwan. Now, the reality is, hopefully that will change. TSMC is building foundries in the US, okay? Other foundries will likely come in. Samsung's building a foundry in Texas, I believe. So that may change, but there's the underlying question here of the politics of it, and I don't know how the politics are will go between China and the US long term. We supply a lot of chips into Chinese-made cell phones. Okay, we can't do to Huawei because they're on the entity list, but in general, it's a very complex situation right now. And that's the best thing I can say is that we have to, as well as everybody else, have to navigate it carefully on all of that. But as a company who has a worldwide market, we have to look to the worldwide markets and pretty much everything out there. So it's one of our more complicated processes is managing the supply chain. And this is one piece of the supply chain management. Let me tell you another piece of it, which is like how many chips to order from a fab. Okay, of what type of chip? Because we get estimates from our customers, but their business changes. And we have to reserve long in advance. And so things always are tricky, okay, on all of this, on actually how you program this. And we are talking about a lot of money going through a fab, okay, on these things, and huge numbers of chips. The cell phone market is around $1 billion a year, slightly less. We're not supplying all of it. But what I'm trying to say is we're talking about, I mean, by the way, that's 1 billion cell phones. So we have, there's actually of the Snapdragon thing, we talked about a chip that's the main one. There's RF chips, okay, that we supply. There's power management chips that we supply. So there's a handful of chips that actually come from us that actually go into typically into a cell phone, as well as other chips from other people. But what I'm trying to say is it's a lot of chips going through the system.
Yeah. One comment I'll make on the sort of design side, or our sort of excellence in delivering silicon and SoCs is Qualcomm is really good at adapting to different fabs, and different fabs have very different characteristics. So it takes a lot of engineering effort to be able to kind of go and hop around between fabs, but we have dedicated to that. And TSMC, Samsung are those two main ones. Like personally, I'd like to see Intel to get up there to be also a third, and our CEO wants the same too. And we'll adapt to that, right? Qualcomm will focus on enabling, leveraging as many fabs as possible. Yeah.
Having both been in the industry for 25 and 37 years, both, could you please explain why the semiconductor industry is cyclical and where we are in that cycle right now?
Why is it cyclical?
It's the rest of it, everything else is cyclical.
Yeah. Industries are cyclical. I don't have a good answer for that. Do you?
No, I mean, seriously, we are driven a lot by the demand for other products. Take the automobile industry. And I said our customers give us estimates, but their business changes too. Okay? And so they give us what they think and what they're planning for. But that doesn't mean that's what they end up having to produce because their climate changes. So that's part of what it is. Plus there's fads that come and go.
Yeah.
We're at the big AI fad right now. Lots of AI capabilities being built out and coming online. That will probably drop at some point.
Yeah.
You know what I'm trying to say? I mean, I'll go back. 15 years ago, you bought a cell phone every year because it was that much better. You don't do that anymore, do you?
Yeah.
Okay. You see what I'm trying?
Yeah.
So,
I mean, I think we're definitely in a peak now with AI driving a lot. Well, the one thing I've found with working at a hardware company is, I think the industry is going to have ebbs and flows. But as sort of engineer, I've seen that even in the troughs and the ebbs, there's still semiconductors companies still invest in the core technology at those times because they know it's going to come back, right? They know it's going to go back up, and they want to be the leader at that time. So I've found from just in personal engineering perspective, I haven't felt kind of threatened in those troughs because there's actually increased investment to be the leader that comes out on the other side.
Hi. I was just wondering what was Qualcomm's intent in acquiring Arduino, and like what's their plan for the future line of like Arduino technology?
It's the question of the day.
Yeah, this is actually pretty straightforward. Our customers, for the most part, have been like the cell phone providers. How many are them these days? They're also very technologically savvy. You know, a Samsung, you know what I'm trying to say, Apple, one of the Chinese OEMs like Oppo, Vivo, Xiaomi, and the others. Auto space, relatively limited number. Now let's look at the IoT space. There's a few big applications, but there are a million others, little ones. So we've been working to get to a platform that is more open source like and common, because we can't do all the apps by any means. There's no way. You need a million companies to do that, to set it up so we can do that. And Arduino is really an entry area into that mass market and changing it so you have the mass market you can face. It's basically going to be the same chips that we put in other things. And by the way, we do have a line of somewhat specialized IoT chips, but it's really moving that into the mass market.
So regarding the design process, with all the various parts of it, like architecture, microarchitecture, model, design, verification, physical design, there seems to be a lot of overlap in terms of like the skills. Like most of them require both hardware and software, and they all involve like really strong knowledge of like semiconductors, how they work, how logic works, that kind of stuff. But there also seems to be quite a bit of overlap. So I'm curious, how do engineers sort of pick between these different fields and which ones they want to choose?
Yeah. It's a good question. I agree there's a lot of overlap, which kind of means there's flexibility. Like, if you go into like design in your first role, you can very easily go into verification or physical design. You can kind of graduate up to architecture. So I see it as a benefit in that it is, it is pretty fluid in terms of like if you have those, skill sets and knowledge base, you can have multiple opportunities. But still there is a lot of people that focus and become kind of the best designer and really become kind of the excellent superstar in that particular role. So I think there's sort of multiple pluses in either direction, and I would just say that there's flexibility, and most companies, including Qualcomm, like if you get hired into one role, they'll want you to do it for at least one project, but if you have interest in other parts and if you're more engaged and more excited about a different role, of course they'll enable you for that, because then you're a better engineer and you contribute to the program that much better. So that's what I've seen. And personally, I've done verification, I've done design, I've done many of these things. So the flexibility is there to move around. Yeah.
I'm just going to add one point. Understand both. You're really valuable. Let's say you stay primarily as a hardware designer. You should actually know the trade-offs and all between the hardware and the software, because that's one of the key things that we always have to deal with. What should go in software? What should go in hardware? And actually what goes more in firmware, and that whole trade-off there.
Mm-hmm.
So I've got one question from in this session. The question is, I've heard that resource-efficient AI relies on low-precision math. Could you elaborate on the impact that different data types, for example, ANT8 versus FP8, has on the Hexa NPU?
I don't know enough about the NPU to answer. I guess the one thing is that we are continually adding improvements across those three: CPU, GPU, NPU. Like what we have on paper today and in the marketplace is like 2 generations behind. Like what we have internally, and data formats is an area that we have increased support in the future. So yeah.
I'm going to add one little thing there. The lower the precision, typically the better power efficiency and the faster. That trades off with somewhat less accuracy, but if you do it right, it's not that bad. So the point is, it's a lot about training, it's a lot about thinking about that architecture and how you optimize for that particular architecture. As I said, you get performance benefits by fewer numbers of bits, but on the other hand, you have to deal with some other issues.
Hi, I think like Qualcomm got into, correct me if I'm wrong, I think Qualcomm got into like the PC space through the acquisition of Nuvia, right? So, and Nuvia was like mainly a data center chip design company. So I'm wondering how come Qualcomm didn't really get into the data center side of it, because considering like now that's a huge market, right, with AI, you know?
Yeah. A little bit about myself. I was part of Nuvia. So I was acquired into Qualcomm because I was part of Nuvia. I mean, Qualcomm has products in the data center, primarily an inference product. Qualcomm has looked at this multiple times to go into the data center, and continues to do that. Like a semiconductor always has to kind of consider the markets where it has strengths in, and what is kind of the best ROI at a given time, right? And it changes decisions on a quarterly basis on a lot of factors. And so, I can't talk about future-looking things, but Qualcomm is always looking at expanding markets, and the aspect of Nuvia, they got a great CPU out of it, right? And it shows, right? You can see it in the market now. And so that was a big win for what Qualcomm already had in established markets and maintaining those markets. Future markets, it just takes a little bit more time to get kind of all the right pieces, not only from the hardware side, but from the software and ecosystem side, to really align to make it the right direction to put a lot of effort into. So.
Yeah, I'm going to just add one thing to that. There are laptops before we came out with the X Elite chip, which is the one you've mostly heard of, that were running based upon cell phone chips, but the oomph in them was not super great. But the point is, they have a lot of the other things that you need. So what we have in the cell phone is we have all the display stuff, you have the USB stuff, you have all that stuff, which is really needed in the laptop. So for us, and we also had the neural processors, the GPUs and all that. So it's really just beefing up those components. Okay, and there's a bunch of other things we had to do, but I'm just saying it's really beefing that stuff up to really hit sort of the sweeter spot on the laptop space. And that's what Nuvia brought a lot in, was a CPU structure that was better performing.
If we don't have further questions, let's give Ed and Joe a round of applause.